So good morning. Today we'll start our lecture on column and struts, and we'll be discussing the three topics mainly: the limitation of the Euler formula, which we have just now derived, and Rankine's formula, and some other empirical formulae and numerical portion. Okay. So first of all, let us summarize what we have learned uh, in the Euler formula. So Euler formula, as you know, Euler's formula. So we determine the critical load, that is PE or PC, is equal to, it is equal to pi square EI divided by LE square, where LE is the effective length. Okay. So we have seen the four end conditions. So let us write here the end conditions. End conditions. What is a crippling load or the buckling load? Crippling oblique buckling load, which we called as the Euler load. Buckling load. And third column we make equivalent length or the effective length. Equivalent or effective length. So this is LE, and here the buckling load is P. So we have considered the four conditions. Number one was both and hinge. Both and hinge or pinned. So in this case, this was pi square EI upon LE square, where LE in this case is L. That is, L is the length of the column. Here you can write LE effective length and L is the length of column. So this is the first condition. In the second condition, one end is fixed, other free. Other free. So in this case, the formula will be pi square EI upon 4L square, where LE is the 2L. If you put here LE square and you put L is equal to 2L, this formula will come. Third condition is both and fixed. Both and fixed. So both and fixed. In this case, it will be 4 pi square EI divided by L square. So in this case, it is L by 2. So if you put here in the general formula L is equal to L by 2, you will get this formula. And the fourth condition was 1 and fixed, 1 and fixed, and other hinge. Okay. So this condition is 2 pi square EI divided by L. So in this case, the equivalent length is L upon 100. So this is a summary of the Euler formula which we have derived, and these are the four conditions in which the different effective length is mentioned. Now next is what are the limitations? So limitations we have discussed in brief. Limitation of Euler theory. Limitations of Euler theory. So we have discussed the 3 points yesterday, and that one is that the column should be perfectly idle, and it should be straight. Okay. So column perfectly idle. It is difficult to obtain a idle situation, perfectly idle. Second point was no initial compression or working. No initial working. No initial working. And number 3 was the slenderness ratio. So this we discuss up to which slenderness ratio the Euler formula is applicable. Slenderness ratio limitation. So these are the 3 limitations because of which we have to use the other formula. So let us say the material is steel, material of the column we take as steel. The yield stress for the steel, yield stress for the steel, it is around 330 megapascal. Okay. And the modulus of elasticity, that is E, it is around 210 gigapascal. Right? Now the Euler formula says that Euler load that is PE, is equal to pi square EI upon L square or LE square, right? So you can write this value of I is equal to A into K square, where K is the radius of least radius of direction, where K is the least radius of gyration. Okay, so you can again rewrite it. You can write it like this: I square E I square E into A divided by LE upon K whole square, right? So this also can be again written as the stress at stress at buckling, that is crippling stress, is equal to Euler load divided by area. Okay. So with this formula, you can bring this EE upon A is equal to pi square E upon LE upon K whole square. So you can write this as E upon A. You can write this as pi square E upon LE upon K. Now, you know the value of pi, you know the value of E. So pi square E value for the steel we take 210 gigapascal, so convert it into megapascal. Okay, and this thing divided by L upon K. This L upon K is what? It is a slenderness ratio. So this value of sigma C, it is given as uh, sigma C. Okay. So sigma C you can write from here the slenderness ratio that is lambda is equal to LE upon K, sorry, L upon K. This thing. So this can be written as from this formula pi square into 2 naught 0 into 10 to power 3 divided by sigma c. So this again if you write, so this will be pi square 2 naught 10 into 10 to the power. Now the sigma C, it is given as 330 megapascal. Okay. So if you uh, uh, calculate this, it comes around 6280.67. So if you calculate the value of L upon K, so this is L upon K square. Okay. So L upon K square. So L upon K, that is slenderness ratio. If you take the square root of this, so it will be roughly 79.25, which is roughly equal to 80. Okay. And we have uh, seen also while defining the columns by ratio, if it is more than that, then it is a long column. So when the slenderness ratio is uh, less than 80, so the when lambda is less than 80, the Euler formula will not be valid. Euler formula is not valid. Okay. So that means it is valid for the slenderness ratio which is greater than 80. Okay. Before that, it is not valid. So we have defined also the ratio that long column is if it is more than 100. So that means if the slenderness ratio is towards more than 80, then the Euler formula is better valid. Okay. So this is a limitation of the Euler formula. So now there is one Euler curve also which we need to understand. Euler's curve. So this is a curve which is drawn between the L upon R ratio, that is slenderness ratio, and the stress, that is P upon E. So on this axis we draw slenderness ratio, on this axis we draw. So it is, this curve is like this. If you come here, it is like this, and from here, okay. So if you extend this curve, so it will be like this, and if you join this, it will cut here. Okay. So A, B, let us define this. A, B. This point is C, where this point is C. And this point is D. Okay. So this range, it will show the short column. Short column. This range it will show intermediate column. Intermediate column. And beyond this, it shows the long column. Okay. So this is a sigma u, that is the ultimate stress. This is a sigma PL, that is a proportional limit. And here you can write sigma u, ultimate compressive stress. Ultimate compressive stress. And sigma PL, proportional limit. Proportional limit. So here it shows inelastic stability. Inelastic. And here it is the elastic stability. And this curve is known as the Euler curve. Okay. So this is also you must know. Now next is the Rankine formula. I think Rankine formula, yeah. So we can write here Rankine formula. So how? Because Euler formula is only there for the more long columns. Okay? So for the Rankine formula, first thing is that it is based upon based upon experimentation. Experimentation. Number two, this is applicable to very short and very long columns. Applicable to very short and very long. Because we have seen 30 to 80 is for the medium columns. So beyond 80, beyond 100, the very long columns stay. So Euler formula is, not very good. So we have to find another formula. Then third is both direct stress, both the direct stress and buckling stress are taking into consideration. Buckling stress have been considered. Okay. So these are the three things. So this formula says that 1 upon P is equal to 1 upon PC plus 1 upon P, where P is the crippling load, P is the crippling load, or I think I should write using the text box. P is equal to crippling load and PC is equal to the compressive or the crushing load, compressive or crushing load, and third is PE, PE or PE is equal to the Euler load. So these are the nomenclature, and this is a Rankine formula. Rankine. So we'll slightly modify this formula and we'll say the PC is equal to sigma C into a sigma C is the yield stress or compressive stress. Sigma C is the yield stress or compressive stress. Compressive. Right? Now, Euler load E, we know pi square EI upon L square, right? So if you put in the Rankine formula, so 1 upon P is equal to PC 1 upon PC, that is sigma C into A plus 1 upon PE. So it will be L square upon pi square EI, right? So if you take the cross multiply this, so it will be pi square EI plus L square sigma C into A divided by sigma C A pi square AI. So if you further solve it, it will be P, and this will be sigma C EA. Pi square you take common, so it will be 1 plus L square sigma C into divided upon pi square. Right. So you can write this I square L upon K. I this will be I A square if you multiplied A here. So you can write this formula as E is equal to sigma C into A divided by 1 plus A into L upon K whole square. So this is a Rankine load where L upon K is the K is nothing but least radius of gyration. So K is the radius of gyration. Radius of gyration. So that we know that I is equal to A K square. So I upon A will be K square here. So this L upon K whole square and this A is a Rankine factor. So A is equal to sigma C upon pi square. This is constant. Okay. So this A is constant and it depends upon material. So it is different for it is known as constant or Rankine constant. Rankine constant depends on material. Depends on material. Right? Say for cast iron, Ti, the value of A is it will be given 1 upon 1600. For wrought iron, because the old structure, you might have seen the columns, they are made up of the wrought iron. It is 1 upon 900, sorry, 9000. For mild steel, the value of A is 1 upon 7500. And for timber, that is wood, for timber, it is 1 upon 750. So this value will be more. That is, it is less strong. But this value will be high, you see, for the steel. So it is less, so that means the strength will be high. Okay. So from here, uh, if we analyze this formula, so you see 1 upon P is equal to 1 upon PC plus 1 upon E. This is a formula, easy way to remember. Okay. Now for the small column, L is small. For the small column, the length is small. So when the length is small, PE, the value of PE will be large because PE is pi square EI upon L square. So PE will large. When PE is large, okay. So when PE is large here, so this value will be smaller. So that means P will be equal to PC. The failure will be by the crushing load. Okay. Then if for the long columns, so long column L will be large. So when L is large, P will be small. When this is small, so this will be appreciable. Okay. So this will be appreciable. So in this case, the P will be equal to P. So that means this formula is valid for small as well as the long columns. Okay. Now these are this is a Rankine formula. So the numericals will be asked. One more formula is there that is known as a Johnson's formula. Johnson formula. So this formula says that P is equal to A into sigma allowable n into L upon P. Okay, where P is the safe load, A is the area of cross section, sigma is the allowable stress, n is a constant which will depend upon the material of the column. N is a constant depends upon column material. Column material. Okay, so for MS, n is equal to 0.005. For wrought iron, n is equal to again same 0. And for my CI cast iron, n is equal to 0.0. Okay. So this is a Johnson's parabolic formula. This is sorry straight line formula. This formula is a straight line formula. This is okay. Then there is one more formula that is known as the Johnson formula. So this Johnson formula, so This formula says that P is equal to a sigma minus R into L upon K. Where R is a constant, it depends upon material. Constant, and it depends upon. Okay? So this formula is also sometimes used. There is one more formula that is known as the Gordon formula. Gordon formula. This formula is P is equal to sigma C into A divided by 1 plus B LE, that is the equivalent length, divided by the D. Where D is the least dia or breadth. Least dia or breadth. Okay. And B is a constant, material constant. So this way, there are the different formulas we use for the case of the Euler columns. So now we are left with the tutorial. So that tutorial I will put on the classroom, so you can do that tutorial. In the meantime, let us try to do one small numerical so that the things are clear. We will do one numerical. Simple numerical. It says what is the minimum width B of a square wooden column. Say it is a wooden column square. That this dimension is given as B. So we have to determine this. This is a wooden column and it is pinned end. So this end is pinned. End is given pinned. End condition क्या हो गई? Pinned. Both ends. So it is given, both ends are pinned and it is a wooden column. Wooden column. The length is given as 3 meters and E value of E is given as 12 GPa. Critical stress sigma C, that is critical stress. Critical stress sigma C, it is given as 9 megapascal. So we have to determine the area. We have to determine this side B. Okay. So we know from the what will be the Euler load or the critical load. E will be equal to pi square EI divided by LE square. In this case, LE is equal to L, so it is 3 meters. So this is given as 12 GPa. Okay. So 12 GPa, that means 12 into 10 to power 3, it is in megapascal. Or this is, sorry, yeah, it is 12 into 10 to power 3 megapascal. So stress is already given in megapascal. So the no, the stress we can calculate as sigma C is equal to PE upon A, right? And A is how much here? PE, A is B square, because it is square, so B into B. So this is given as 9. So therefore, this implies P is equal to 9 B square. So this you can keep here. So 9B square is equal to pi square is equal to E is given as 12 into 10 to power 3 and I is given. I you can calculate. L is 3 meter square. Okay. So meter you convert into millimeter because you are taking everything in megapascal. So I will be equal to I is for the BD cube upon 12. So B into D is again B is B, BD cube upon 12. So you can put this value over here. Okay. So it will be pi square into 12 10 to power 3. This will be B4 divided by 3000 square. So you can get from this equation the value of B square. So B square will come 8207 roughly. Okay. So B by taking the square root, so it will be 90.0. So this is how we use the Euler formula. So you will be given the end condition, you will be given the other condition in the numerical, and you have to solve it. So I'll stop my lecture over here. So thank you very much for your patient listening for a long time. So thank you very much.